Alright, welcome to our first video for Chapter 8, Chemical Equations and Reactions. So we're going to be talking about chemical equations, or chemical reactions also, here to start off with. But we should start talking about physical reactions. So a physical reaction is just a change in appearance. It's not changing what the material is. A great example is melting of ice. As you melt the ice, it becomes liquid water, but it's still H2O on both parts. So nothing has changed. It's still the same material. You could also think about cutting wood. You're breaking the wood up into smaller pieces, and it's still wood though. It's still the same material going on. Now, a chemical reaction is going to change what the material is. It's going to change the substance. So during a chemical reaction, you're going to be creating something new, something different that wasn't there before. So things are changing what they are. A good example is burning paper. So as the paper burns, what's left behind, the black ashy part, is not the same material. It crumbles, it's brittle, it doesn't have the strength that paper does to hold together. So all these properties are different because it is a different substance. Another example we saw is putting sodium in water. We saw a great explosion come out of that. Definitely a reaction. We saw gases coming off. Hydrogen gas was being released. The gas ignited and boom. We tested the pH of the water before the reaction and after the reaction. And before it was neutral, and after we saw a much higher pH. It was a very basic solution because it created sodium hydroxide in the solution, which is a base. So we saw a lot of changes going on there. Definitely not the same stuff anymore. Another example you can think about is eating food. When you're eating and going through that digestion process, your stomach is breaking down the food and changing it. And when it comes out, it is definitely different than how it went in. You have created something new and done a chemical reaction. Evidence of chemical reactions. A really good one is a change in color. Just like the burning of the paper, we see color change. That's normally a really good indicator of a chemical reaction. Another example of that is iron rusting. As the iron reacts with the oxygen and it creates the iron 3 oxide on the surface, we see a color change. It's turning to that reddish brown color. We also see texture change because the rust is ionic compound, right? So it's brittle and it's not as strong and malleable as the iron was on its own. So again, we see some good visual changes with that. Gases being produced is another good evidence. Burning something, you see the smoke coming off and things like that. With this reaction here, we have zinc in hydrochloric acid, HCl. And as they react, hydrogen gas is released. That's the bubbles that are forming there. It's like, hey, those bubbles weren't there before. That's something new. This must be a chemical reaction. Forming of solids from two solutions. So if you remember when we talked about solutions, we have things dissolving in water. When we talked about ionic compounds dissolving in water, like table salt, sodium chloride. If we put salt in water, you get salt water, right? Nothing has changed. There's still salt, there's still water. That is just a physical reaction. So if you're just dissolving something in water, that is only a physical reaction. Nothing new has been formed. But if we have two of those solutions that combine together, so here's an example of potassium iodide is being added into lead 2 nitrate. And so both of those are in solution. Water has pulled apart those ions and they're floating around. But when we combine the two of them, the lead 2 in the beaker combines with the iodide that was added to it, and they lock together, and water can't pull them apart, and it makes that yellow solid there of lead to iodide. So that yellow solid we would call the precipitate. So this reaction formed a yellow precipitate, which we would identify as the solid lead to iodide. So we'll see a lot of reactions that form precipitates, and we'll have rules that will go through and help us predict when things are going to be insoluble in water, which means that they don't dissolve, as opposed to things that are soluble. Heat can be a sign of a chemical reaction, like burning stuff, but you really got to think about the source. You know, I can go like this, and I can keep my hands up, and I'm not changing my skin. It's still skin there. No chemical reaction has gone on there, even though I'm producing heat. So think about the source of the heat when you're looking at the reaction. Light can also be given off, just like burning the paper. We see light coming off, but there can be physical reactions that give off light. A light bulb, for instance, has the electricity, the electrons moving through the wire. As the electrons are forced through the tungsten in the filament of the bulb, there's more resistance, and the electrons being pushed through there create friction, and that creates the heat and light that comes off of a light bulb. So think about the sources of the heat and the light as you look for evidence of chemical reactions. So when we're writing chemical equations to show this reaction, we will have symbols that we use to denote what state of matter they are in. So if it is a solid, down we'll put a little s in parentheses as a subscript down below the compound to show what it is. If it's a liquid, we'll put a lowercase l, but this font is not very good. It should be a cursive L, because a lowercase l like this would look like a 1 and would be confusing. So we use a little g for gas in parentheses, and if it's dissolved in water, we call it aqueous. So just like aquarium and aquatic and Aquarius, the constellation, the water bearer, all those things dealing with water. If it's dissolved in water, it's aqueous. That is a lot different than being a liquid. If we have table salt, sodium chloride, and we put it in, dissolve it in water, the water pulls it apart, and that would be aqueous. To make liquid sodium chloride, we'd have to heat it up a couple thousand degrees. We know ionic compounds have really high melting points, and that's a different process than being aqueous. Now, when we talk about chemical reactions, the things that we start with are called reactants. So on that left side of our equation, the things that we're starting with are the reactants. The things that we end up with are the products. So they are produced from the chemical reaction. So what things are coming out of it are the products. We have an arrow in between those two to denote the direction of the reaction. And normally we have the arrow moving to the right. You may also have a double arrow like this, which means it's a reversible reaction. It can go both ways. Now, we also put some symbols over the arrow sometimes, and that can show special circumstances. If there's energy needed for the reaction, if there's the delta shows a change in energy. Heat pretty much means the same thing there. And then if you see a temperature like the 76 degrees Celsius, that's the temperature that it is required to have that reaction start. So those are some things you'll see over top of the arrows. Whoops, let's go back here and bring up some examples. So I wanted to write out some of these examples, and starting with water, we can have H2O and oops, I'm not green. And if we have H2O, that's a liquid. So here's the cursive L that we would use in the parentheses to show that a reaction is taking place. So if I have liquid water, and then I add some energy to it, so I need some electricity is what we would use, and it would break up the water. And it would break up the water into hydrogen gas, and we know hydrogen gas is diatomic, so we would have two hydrogens there, and I would say it's a gas by putting a little G like that. And then we would also create oxygen gas, which we also know is diatomic, and we put the little G there with it. So we read this across. We started with liquid water, we added some energy to it, and we broke it up into hydrogen gas and oxygen gas. Now some of you are going to be looking at this and be like, hey, how can we have two oxygens on one side over here and we only have one on the other? Well, we will work that out eventually. We'll talk about balancing equations in our next video, but for right now, we know that these are the right formulas. They're diatomic, and we'll make the ratios work out later. We'll show how that will work. Another example we could talk about is the rust. We talked about rust in the video. We have iron that is a solid. So we have a little S down there, and it's going to react with oxygen gas. And it is going to react and form iron 3 oxide. So iron has a +3 charge, oxygen has a -2 charge. So here's our correct formula for iron 3 oxide, and that would be a solid. And again, we'll talk about the balancing later and how we can work out the quantities of these, but these are the right formulas. These are how they're going to react. We'll change the quantity, how many irons we start with on our reactant side. So remember, these are the reactants, and what we get is the products. Another one we saw in the video was the lead 2 nitrate. So lead 2 has a +2 charge, nitrate is a -1. So we know the correct formula should be like this. This was dissolved in water, so we would say it's aqueous. Now we had another solution of potassium iodide, and that was also dissolved in water. Potassium's a +1, iodine's a -1. And we combine those two. And so we will think of our positive-negative combinations. I'm not going to have two positives come together, but I can have the potassium meet up with the nitrate. And then the other combination would be the lead 2 with the iodide. Now, we saw the picture of this, that by mixing these two, we made a precipitate. One of these two products is a solid. They lock together so well that water can't pull them apart. Now there are rules that we'll talk about and go through, and you can predict which one is going to be soluble or not. But right now I'll tell you a couple of quick, easy rules. Nitrate is always soluble. It doesn't matter what it's with. Whatever nitrate is going to get pulled apart by the water and be aqueous. We could also look at the alkali metals. All the alkali metals are always soluble. The one exception of that is lithium fluoride. Everything else will always be soluble. So potassium, whatever, is going to be soluble in water. So if there was a precipitate formed, I know it's not from the potassium nitrate. It has to be the lead 2 iodide is my precipitate, and it made a solid. So again, we'll talk about balancing of these in the next video as we go. The last one I'm going to show you is ammonia. So ammonia is NH3, and that is a gas. And we're going to react that with water. So if we put ammonia gas, have it dissolved in water, liquid water there. Now here is an example of when we have a double arrow. This is a reversible reaction. What it will make is ammonium hydroxide. And this is aqueous. This is dissolved in water. So we're going back and forth between these two sides. We have molecules here which do not have charges, and then we have ions in solution. This is aqueous, so it's an electrolyte. We have ions in solution here, and they are constantly kind of breaking and reforming and going back and forth between these two. So that's what the double arrow means, is that you'll have both sides in the reaction. They may not be even. We may have more abundance of the ions here than the molecules, but that depends on the reaction. But the double arrow means that it can go both directions. So those are some examples of how to write chemical reactions. We're going to be writing the equations out, so you got to remember putting your charges, all the stuff that we learned before. We're still building on that and using all that information. So go ahead and get busy on your homework, and we'll do some more practice in class.